Okay, everyone, welcome to the first of what will probably be two video lectures for Chapter 18. So you'll remember that in Chapter 17, we introduced the concept of the t-test. And in that chapter, we dealt with what's called a one-sample t-test. Either we had a mean from one sample that we compared to a hypothesized null mean, or we were looking at the mean difference between say before and after or pre and post test scores, and we were comparing the mean difference to a hypothesized null mean difference. That second example is what's called a matched pairs design, but both of those are examples of one sample t-test. In this chapter, chapter 18, we're going to be dealing with situations where we're comparing two separate means and two independent sample means. Okay, it's a little bit different situation than chapter 17. All right, so we're dealing with two sample situations, and one of the key points here is that we have samples that are completely independent of one another. There's no linkage between them at all. Collected maybe entirely different places, different times, whatever, but they are both completely independent of the other. And that's why we need what's called a two-sample t-test. So basically, we're looking to see if those two samples are different, not only from each other, but also from a hypothesized null mean. Okay, so there are times, lots of times actually, when we need to compare two treatments or two conditions. So what is a treatment, first of all? Well, let's say we're doing like a clinical study. And you've got one group of your subjects that you've separated out as the placebo group. They get a placebo or a sugar pill. The other group actually gets the drug that's being tested. That would be called the treatment group. Likewise, you could take that group and divide it up into smaller subgroups. Each one gets a different concentration of the drug. So the different concentrations would be considered treatments as well. Okay. So we very often find ourselves needing to compare two treatments or two conditions, and those treatments or conditions need to be independent from one another in order to use a two-sample t-test. All right. So independent means, again, the individuals in both of your samples are chosen separately from each other. There's no linkage whatsoever between them. And that's a key difference compared to the matched pairs design that we looked at in Chapter 17, where you had maybe two data points for each subject. They're linked together because they are for that one subject. Okay, so in the case of a two-sample t-test, we have two independent random samples, and basically we're going to be testing whether or not they come from two populations. We'll get to that more in a little bit, but recall that in the case of a t-test, we don't know either what the population mean is or the population standard deviation. And not knowing that population standard deviation is precisely why we're doing a t-test and not using a z-score or calculating a z-score. Okay, so what we're going to do is, let's say we have two populations, and one population is characterized by mean 1 and standard deviation 1, and the other population is characterized by mean 2 and standard deviation 2. And we don't know any of these numbers, right? So what we're going to do is use our mean of sample 1 and its standard deviation to estimate the mean and standard deviation of population 1. And we'll use the sample mean, or the mean of sample 2 and its standard deviation to estimate the unknown mean and standard deviation of population 2. Okay? All right, so that's the idea here. Now, a couple of sort of assumptions or things that we need to keep in mind. Both of our populations, again, should be normally distributed. If they're not, however, as long as we have a sample size basically of greater than 40, then we probably don't have to worry about whether our populations are normally distributed. So central limit theorem allows us to get a normally distributed sampling distribution even from a skewed population distribution, but you got to have a large enough sample to be able to do that. All right, now in the case of a t-test, a two-sample t-test, it's really sufficient enough that both distributions are at least shaped in a similar way. All right, but again, good rule of thumb is to have a large enough sample so that you're pretty much guaranteeing that your sampling distributions are going to be normal. And the way you do that is by trying to have at least a sample size of 40 or more. Okay, so again, the general idea here is that we need to calculate a t-statistic, a test statistic. And we look that up on a table, and we will see at a certain confidence level what p-value that corresponds to. So our calculation of t is a little more complicated here. Let me fill this in like I always have to do on the iPad for whatever reason. Okay, minus u minus mu2. All right. Okay, so to calculate our test statistic here, what we're doing is taking one sample mean and subtracting its value from the other sample mean. So we're getting a difference of our two sample means. Then we're going to subtract from that the hypothesized difference in our two population means, mu1 and mu2. All right, now in practice, in most cases, this is going to be 0. We're going to be assuming under our null hypothesis that there's no difference in our population means, which really means we only have one population that we're dealing with. So usually this is going to equal 0, all right, that term. Now our denominator is the standard error of the mean, like we calculated for a one sample t-test. But there, we just took the standard deviation of our sample and divided by the square root of our sample size. Well, here we have to take into account that we have two samples, and we have to do the standard error for both of them. So we take the standard deviation of sample 1, square it, and divide that by the size of sample 1. We take the standard deviation of sample 2, square it, and divide by sample 2's n, or sample size. We add those two numbers and then take their square root. And that is the standard error of the mean for a two-sample t-test. All right, now this formula down here, which is quite complicated, okay? This is how we calculate degrees of freedom in the case of a two-sample t-test. Let me just fill this stuff in like that. Okay, oops, forgot plus sign. Okay. I'm not going to ask you to calculate this by hand. It's just too complicated. Okay, so either I will give you the degrees of freedom, or to be in the problem or whatever, but or Minitab will calculate it for you, but you won't have to calculate this by hand. So don't worry about that. All right, it's a lot more complicated than what we saw in the last chapter, where the degrees of freedom was simply sample size minus 1. Okay, so don't worry about that formula there. All right, so let's talk about this two-sample t-test. So we have two independent random samples, and our null hypothesis is going to be that the mean of population 1 equals the mean of population 2. Another way to think of it, the difference between those two populations is 0. So if we're assuming that our two populations have the same mean, or that the difference between their means is 0, then we're assuming we just have one population, or we're stating rather that we have one population. So what we're trying to do with our two samples is test whether or not they come from one population, that population, or from two separate populations. Maybe one of them comes from our null population, the other comes from a different population. All right, so again, we have to calculate our test statistic. Let me fill this in, okay. There we go. All right, so again, this is how we calculate our t-statistic. So sample mean 1 minus sample mean 2, that difference minus the hypothesized difference in our population means, which as I said is typically going to be 0, right? That means we can discount this altogether, okay? So we can simplify the formula then for calculating t to this. We simply take the difference between our sample means and divide it by the standard error of the mean, which is this denominator term right here. So my point is, we don't have to worry about this. We can ignore this in most cases, because in most cases, we're assuming, our null hypothesis is assuming that there's no difference between our population means. So you take this difference of the sample means, subtract 0 from it. It doesn't change anything, does it? You still have that difference. That's why we can discount this. Okay, so we get our test statistic. We then use table C to find a p-value, and then we can either accept or reject our null hypothesis. Of course, keeping in mind that we have to determine whether or not we have a one-sided or a two-sided alternative. Okay, so let's look at an example. Does smoking damage the lungs of children exposed to parental smoking? So one of the ways to measure lung capacity is through what's called forced vital capacity, or FVC. This is simply the volume of air in milliliters that a person can expel over a 6-second period. So you'd expect at the outset that if somebody's a smoker, and given what we know about smoking and how it affects breathing, you might expect that smoking could only reduce forced vital capacity, reduce lung capacity. It certainly isn't going to improve it. So this is going to be a one-sided alternative, okay? We're expecting that our mean for a group exposed to smoking or cigarette smoke is probably going to be lower in terms of forced vital capacity than others not exposed to cigarette smoke. You wouldn't expect it to be higher because cigarette smoke is a bad thing. So they took forced vital capacity, They took forced vital capacity and obtained that or measured it for a sample of children not exposed to parental smoking, so not exposed to secondhand smoke, and a sample of children who probably were raised in smoking households and were exposed to secondhand smoke. Here we have our summary table. Parent smoking status, yes, no. You can see that children who lived with parents who smoked had a 75.5 average FVC, standard deviation, sample size of 30, whereas children who were not exposed to secondhand smoke had a forced vital capacity of 88.2, standard deviation and sample size of 30. So our question then is this difference that we see here between these forced vital capacities, these averages, these sample averages, is that just random variation, or is it due to some negative effect of smoking on forced vital capacity? All right, so our null hypothesis is that the population mean for smokers in terms of forced vital capacity is the same as it is for non-smokers. In other words, the difference between smokers and non-smokers for FVC would be 0. The alternative is that smokers would have a lower forced vital capacity, or that the difference between them would be negative, right? Negative. Why negative? Because smoking should reduce or take in the negative direction forced vital capacity, all right? So it's definitely going to be a one-sided test here. Okay, so let's run through it. All right, so again, we have our summary statistic table right here that we're going to need, okay? And so I'm going to fill this in again. We have the mean of smokers minus the mean of non-smokers, okay? And we're going to divide that by the standard error of the mean. So that's our denominator here. So again, we have the standard deviation for smokers, right, of 9.3, and there you see it, 9.3 squared over the sample size, which is 30. We have the standard deviation for non-smokers, which is 15.1 right here, squared, divided by the sample size there, also 30, right? We got to add those together. Then we take the square root of all that, and we end up with 3.24 as our denominator. The difference in our sample means is 75.5 minus 88.2, or negative 12.7. So you do that math, it works out we have a test statistic of minus 3.92. So remember that your t-statistic, like a z-score, is a measure of standard deviations. So we're talking about a difference between the forced vital capacities of smokers and non-smokers that on the sampling distribution for this lies almost 4 standard deviations to the left of our hypothesized null mean of 0. So if our null mean of 0 is right there, we are way over here somewhere, right? Way over there. And so because you know that 2 standard deviations will give you a p-value of about 0.05, we're almost twice as many standard deviations away, so you know your p-value is going to be much, much less than 0.05. So just by looking at that number, you know this is significant. That difference is significant, all right? Okay, and again, here's the calculation for degrees of freedom, which again, I'm not going to ask you to do. I'm just sort of filling it in here because it bugs me that it's not filled in. All right. Okay. All right, so you work out all that math, you end up with a degrees of freedom of 48. So again, the degrees of freedom is going to tell you what row of the table you need to look at when you're trying to find your p-value. All right, so in table C, for degrees of freedom of 40, because there isn't a row for 48, so you get to go to the next lower one, which in this case is 40, we find that our p-value lies between 3.551 and, I'm sorry, the absolute value of our test statistic is greater than 3.551. I'm going to show you in a minute. If you look at that table, row 40 of that table, you go all the way to the right, the last number is 3.551. Well, we have 3.92. The absolute value here of this is 3.92. It's to the right of 3.551. It's off the table. So 3.551 corresponds to a p-value of 0.0005, and p-values get smaller as you go to the right on the table, so we know our p-value is smaller than 0.00005. In fact, Main-Tab would calculate it at 0.00014. So this is very highly significant. We are well within our rights to reject that null hypothesis here, okay? So in doing that, we are concluding that lung capacity is significantly impaired in children exposed to parental smoking compared to the FVC, or forced vital capacity, of students or children not exposed to parental smoking. So we have a test statistic of 3.92. Now again, it says minus, but that's just to tell you that it's on the left-hand side of your curve. For the table, you have to take the absolute value of this. There's no negative numbers, so you have to look for 3.92. So let's do that. So here we are with degrees of freedom of 40. And so you follow that row all the way over, looking for 3.92, and you don't find it. The last number is 3.551, and for a one-sided test, that corresponds to a p-value of 0.005. So again, our actual test statistic is way off to the right over here, so we know that our p-value is smaller than 0.0005. It's 0.00014, actually. Again, very highly significant, okay? All right. Now, let's talk about, let's look at some examples of appropriate null hypotheses here. So let me fix this here real quick. Okay. Oops. Wow, it's weird how this thing just leaves out Greek letters. All right. So these are various different possible null hypotheses, and we're going to look to see which one of these is correct. There's only one of them that is actually correct. Okay, so first of all, we're looking at geckos. So geckos are lizards with specialized toe pads that enable them to easily climb even slick surfaces. Researchers wanted to know if male and female geckos differ significantly in the size of their toe pads. In a random sample of Tokay geckos, they find that the mean toe pad area is 6 centimeters square for males and 5.3 centimeters squared for females. What is the appropriate null hypothesis here? Well, you can discount a couple of these options, A through E, automatically if you remember that null hypotheses are always about populations, and populations are described through parameters. Greek letters, for example. So here we have, for example, a sample mean, sample means. Null hypotheses are never about sample means. They're always about population means. So you can discount those two automatically, okay? All right, let's look at E, for example. E actually contains data. So look, 5.36, a difference of 0.7. That's data from our data set. If you're formulating a hypothesis using data from your data set, you're forming the hypothesis after you've collected the data, which is backwards. We never include data from our data set in our null hypotheses, so we can discount that one. Now we have a choice between C and D. So let's look at D. Here you're looking at the mean difference of male versus female toe pad area. So maybe you have 15 males and you find their toe pad areas. You have 15 females, you find theirs, and you subtract them from each other, okay? This would be a matched pairs design, and so that's not what we're looking at. We're not looking at mean difference here. We're looking at the difference between the average for males here and the average for females. So this is one sample, that's a second sample, you subtract them from each other. So this is a matched pairs design. C is the correct one. All right. Okay. Now, another question. Should the alternative hypothesis be one-sided or two-sided? Well, here you have to go back and read the problem. It says researchers in that second sentence, researchers want to know if male and female geckos differ significantly in the size of their toe pads. It did not specify a direction. It didn't specify that males might have more or less surface area than females. It could be in this case that you might think that males will be a larger animal and therefore more surface area, but maybe in geckos, males are on average smaller than females. Who knows? So because a direction wasn't specified, this is going to be a two-sided alternative. Okay, let's talk about confidence intervals now. So because we have two independent samples, we're going to use the difference between both sample averages, right? So, one more. Sample mean 1 minus sample mean 2 to estimate the difference in our population means, okay? So, again, a confidence interval is an area between two limits, right? It's an area of our curve within which we are a level C confident that our true population mean lies. So if this is 95% confidence interval, we're 95% certain that our population mean lies between these two numbers, right? Or within the interval. Okay, so remember that to do this, to calculate a confidence interval, we have to calculate a margin of error. And in this case, the margin of error equals the critical value of our test statistic, t, that we look up in a table for a given confidence level, multiplied by the standard error of the mean. Okay? All right, so this value of t we're going to look up. If we're using 95% confidence, we look up the appropriate value for that. If we're using 99% confidence, we look up the appropriate value for that in the table. And then simply multiply that by the standard error of the mean for our two samples. And that's our margin of error. It gives us 1/2 of the confidence interval, right? So 2 times your margin equals your confidence interval, right? 2 times your margin equals your confidence interval. That's why we're calculating margin of error. Okay, so let's take a look at an example of a t-test where we sort of put all this together, all right? So the question is, how does pesticide help seedling growth? Seeds are randomly assigned to be planted in pots with soil treated with pesticide or in pots with untreated soil. So seedling growth in millimeters is recorded after 2 weeks. So the seedlings that are planted in pots with soil treated with pesticide, that's our treatment group. Those in the untreated soil, that's our control group, okay? So our treatment group is here on the left. You see we have treatment 21, sample size 21. We have 21 measurements here of plant growth in millimeters over that 2-week period. Control group, we had 23. Here are those 23 numbers in terms of individual measurements, or measurements for each plant in terms of their growth. All right, so confidence interval. A 95% confidence interval then, okay, it's going to be the difference between our sample means plus or minus our test statistic times the standard error of the mean, okay? All right, now, the degrees of freedom calculation, which I told you don't have to worry about, is over here on the right. Basically, if you plug in your standard deviations and your sample sizes over here, you end up with degrees of freedom of 37.86. So that again is going to tell you what row of the table to look at. But because there isn't a 37 or a 38 row on the table, we're going to use degrees of freedom of 30. Okay. All right, so let's do our calculation for margin of error. So we have mean 1 minus mean 2. So we have 51.48 minus 41.52, all right? And that's going to be plus or minus our critical value of t. Now we're assuming we're doing this at 95% confidence. So if you look at the table, 95% confidence gives you a critical value of t at 30 degrees of freedom of 2.042. And that's where this number comes from, right? That's our t. Okay, multiply that by the standard error of the mean, which again is going to be the standard deviation of sample 1 squared over the sample size for sample 1, all right? Plus the standard deviation for sample 2 squared over sample 2 sample size. So add those, take square root, and you get 9.96 plus or minus a margin of error of 8.8. All right, so basically we know, for example, let me do some calculation here on a calculator. If you take 9.96 and subtract 8.8 from it, you get a margin of error, a confidence interval, basically of 1.16. Let me do that math real quick. 9.96 plus 8.8 to, 18.46. So this is our 95% confidence interval. And you know that our hypothesized null mean of 0 lies outside that. It's just below it. So because it's not within the 95% confidence interval, what do we know? Without even looking at a p-value, we know that the difference between our sample means, right, the treatment group and the control group, the difference in their growth is significantly different from 0. So in this case, we know our p-value is going to be less than 0.05. If we're doing this at 95%, our alpha is 0.05. Our p-value is going to be less than that because our population mean lies outside our confidence interval. And so now all we need to do is find out what that p-value is going to be. We can do that by looking up on a table, or we can just have Minitab calculate it for us. So here we have output from Minitab. All right. So for degrees of freedom of 38, our margin of error again is going to roughly equal 8.72. Now there's a little bit of rounding error here because we couldn't use 38. It wasn't in our table, so we had to use 30. So we had a little bit different. We had 8.8 versus 8.72, but that difference is usually not any more than rounding error, so it's okay. So we're 95% confident that using pesticide yields seedlings that are 1.2 to 18.7 millimeters longer on average after 2 weeks, okay? And if you look at the output, the Minitab output for the 2-sample t-test, you see we have a p-value of 0.027. So it's not super highly significant, but it's significant. It's less than 0.05. So we know, we can confidently state that that difference in those sample means is not just random variation. It's likely a real effect due to our treatment. Treating the soil with pesticide knocks down insect and probably annelid and roundworm pests that would sort of limit plant growth, right? Without those pests around, because of the pesticides, the plants grow better. All right, I think I'm actually going to get this done in one video lecture, so that's good. Okay, so next thing to talk about is robustness. So I said that a 1-sample t-test is fairly robust, and what that means is that it's not highly sensitive to non-normality, skewness, or outliers, right, within certain limits. And basically we said that if you have a normally distributed population, you could have a sample size of less than 15 and you can use the t-test no problem. But with mild skew, you probably need to have a sample size of 15 to 40. And with wildly skewed population distribution, you're going to need a sample size of greater than 40. Okay, and so those rules generally hold true here as well with a 2-sample t-test. As a guideline, a general sort of rule of thumb though, for a 2-sample t-test, we want to have a combined sample size, so sample 1 added to sample 2, total sample size of 40 or more, and that will allow you to not have to worry about whether the population is skewed or not. You can get around that problem altogether, and again, that's because of central limit theorem. The larger the sample size, the more normal the sampling distribution is shaped, okay? All right, one warning about this, especially when you start using Minitab to do 2-sample t-tests. There's an option in Minitab, and there's a different kind of version of this 2-sample t-test called the pooled 2-sample t procedure, okay? So we have 2 versions then of the 2-sample t-test. One of them assumes that the variances amongst your 2 samples or within your 2 samples are equal. That is the pooled variance option. The other option does not assume that they have equal variance. that the variation within the two samples is about the same, okay? So one option assumes it is, that's the pooled, the equal variance. The other, the unequal variance, assumes that it's not. Now, the thing is that this assumption of equal variance is somewhat difficult to check. It's hard to verify. So if you have no idea if the variances of your two samples are the same, see here you have two very different variances, then it's best to use the unequal variance or the non-pooled option. In Minitab, you'll be given that option when you do, or you can see that option in the test options when you go to do a t-test. And it's probably best just to not check the box for pooled variance, to leave it unchecked, in which case you are not assuming equal variances. That's probably the safe thing to do, okay? It's the more conservative approach. It should make your results a little bit more reliable. All right, so let's review our T procedures here a little bit. So, one sample T procedure. That was in chapter 17. There, we are doing statistical inference about a population mean, right? Okay, we have one sample summarized by its mean and the standard deviation, S, and we're using that to infer something about the population mean and the population standard deviation, neither of which are known. In a matched pairs T procedure, also a one sample, we have two paired data sets from a matched pairs design, maybe pretest and post-test scores, for example, and from the pairwise differences, the mean difference, in other words, and the standard deviation of that mean difference, we are estimating the population mean difference and the population standard deviation of the difference, both of which are unknown. So this is the parameter that we're inferring about. With a two sample procedure, we are looking at differences between population 1, the mean of population 1 and the mean of population 2. So we have two independent random samples, unrelated individuals in the two samples. We summarize each sample separately. So sample 1 has mean 1 and standard deviation 1. Sample 2 has mean 2 and standard deviation 2. And we're using these to infer about the population means and standard deviations, which again are unknown. All right. So you have to know what the scenario is for which you're analyzing the data in order to know if you're doing a one sample matched pairs or a two sample T procedure. Okay, it's important. If you use the wrong test on the wrong data set, you're not going to get valid results. Okay, so let's look at some examples here and figure out what kind of t-test we might do or use in these four scenarios. So, upper left, right, is blood pressure altered by use of an oral contraceptive, comparing a sample of women not using an OC with a sample of women taking it. Well, this would seem to suggest we have two independent samples, one group of women who are on a contraceptive and another group entirely, could be from a different city even or different country, not on an oral contraceptive. Those are two independent samples, so that would be a two sample t-test. All right, so this is a two sample t-test. All right, below that, average cholesterol level in general adult population is 175 milligrams per deciliter. Take a sample of adults with high cholesterol parents. Is the mean cholesterol level higher in this population? You have one sample from one population. It's not even a matched pairs. It's just a single sample, one sample from each person in that sample at one time. So that's a one sample t-test. One sample simple. It's not a matched pairs. All right. Upper right. Does bread lose vitamin with storage? Take a sample of bread loaves and compare vitamin content right after baking and again 3 days later. So the idea is here you take a sample of bread loaves out of an oven, you take samples from them right then and there, you let them sit for 3 days, and you come back to those same sample of bread loaves 3 days later and take another sample. This is a one sample matched pairs design because each bread loaf is measured twice. You have two measurements for each bread loaf. One at the end of baking, one 3 days later. That's a matched pairs. All right, so this is a matched pairs. Final one. Does bread lose vitamin with storage? Take a sample of bread loaves just baked and a sample of bread loaves stored for 3 days and compare vitamin content. So here you have a sample that was just baked and a different sample measured at the same time that was baked 3 days before. You have two separate samples, right? Two separate samples. So that's going to be a two sample t-test, all right? So you have to be able to read these descriptions and the scenarios and figure out what is the correct test to use. That is one of the more challenging aspects of statistical analysis, understanding and knowing what is the correct test to use for what situation. If you use the wrong test, say try and use a one sample t-test on a two sample situation, you will not get valid results, okay? So you have to be careful about that. All right, so that is it then for chapter